Hello friends, I am Satyendra and today in this video I am going to explain you about the anomalous Zeeman effect. Okay, so let's see it. Okay, so the splitting of spectral lines in fairly weak magnetic fields show in general to have a structure and is more complex than the three line observed in normal Zeeman effect. Okay, and this phenomena is known as anomalous Zeeman effect. The anomalous Zeeman effect can be explained on the basis of vector atom model by considering the electron spin in addition to the orbital motion of the electron. Okay, so in anomalous Zeeman effect, the magnetic field used is a weak magnetic field, and this shows a even more complex structure than the three line structure which is observed in the normal Zeeman effect. Okay, and in order to explain the anomalous Zeeman effect, the electron spin as well as the orbital motion of the electron is taken into consideration. Okay. Now let's look at the explanation of the anomalous Zeeman effect. Okay, so we all know that an atomic level can be well specified by its values of angular momenta L, S and J. Okay, in in the atomic system, if the atomic system is placed in weak magnetic field directed to the z direction, the interaction energy is given by, okay, in this case, so so if if you place the electron atom in the weak magnetic field, then the interaction energy is given by this formula, and how this formula came is quite easy to understand. So let's see. So and this is the potential energy, okay, which is called the interaction energy. So this is the energy due to the interaction. Okay, so this is the interaction energy due to orbital magnetic dipole moment and external magnetic field. Okay, and this is the interaction energy due to spin magnetic dipole moment and the external magnetic field. Okay, so the interaction energy is the sum of these two interaction energies. Okay, so how, what is this stuff, what this stuff is actually is, let's see. So we all know that okay, in consider that there is a nucleus and this is the atom. Okay, and this is the path where the electron revolves around the atom. Okay, so the atom can revolve around the orbital path. Okay, this will give rise to the angular momentum L. Okay, and due to this orbital motion, there will be the magnetic moment associated with this orbital motion, and that magnetic moment is actually called mu L, and that is equals to minus E upon 2m L. Okay, this is that much. Okay, and we also know that each electron, in addition to the orbital spin, in addition to the orbital motion, it also have the spin motion. Okay, so it also has the spin motion and it spins around its own axis. Okay, so due to the spin motion, okay, due to the spin motion of the electron, it can be either up or down spin, okay, of the electron. Okay, so if the electron spins, okay, if it spins, okay, then let the spin angular momenta is s, then the spin magnetic moment is mu s, and that is equals to minus E over m s. Okay, so this is the magnetic moment associated with the spin motion of the electron. Okay, now there is another important concept that you have to understand, and that is, see, if there is any magnetic field, okay, B, and if you place a magnet, okay, here if you place the magnet and the angle between the magnetic field and the magnet is theta, okay, then and if the this magnet has the dipole moment, that is mu, then the potential energy of this magnet in the presence of this magnetic field mu is, this potential energy is minus mu dot B. This is the dot product. So this is the potential energy of the magnet in the field, in the presence of magnetic field, and this potential energy is sometimes called the interaction energy. Okay, so this is called, either this is called potential energy or interaction energy. Okay friends, so this thing is clear to you, right? So at this point now you can clearly understand that this is the potential energy due to the interaction between orbital magnetic moment and the field, and this is the potential energy due to spin magnetic moment and the magnetic field B. Okay, and this is the sum of those two potential energy, and this is called the interaction energy. Okay, now the above equation can be easily written like this by taking B naught out. Okay, now I have already explained you that the the orbital magnetic moment is written in this by this formula, and the spin magnetic moment is written by this formula. I will plug these two formula in this here, and this will be plugged here, and finally so the equation number 1 will come to this form. Okay, and then again I can solve it further like this, and then I will take out this term common, and I will left only with this much equation. Now in this equation there are some important concepts to understand, that we have used, if since the magnetic field B0 is weak and the coupling L plus 2s is quite strong, okay, that means spin and spin orbit coupling is quite strong, and so this term cannot be broken down into two terms. So this cannot be broken into the two terms. Okay, so let's put this quantity equals to j g into j. Okay, where j equals to L plus s. Okay, that is the total angular momentum, and this came from the Wigner-Eckart theorem. Okay, I'm not going to take you in the details of the Wigner theorem because that will divert us from this current topic. Now with this substitution, okay, equation number 2 will come to this form. Okay, and here there is a term g is called the Linde G factor. Okay, this is called the Linde G factor, or this is also called the splitting factor. Okay, this is also called the splitting factor. I will explain you why this is called the splitting factor. Okay, now the value of G is given by this formula. Okay, and you have to remember this formula. The derivation is formula is of this formula is not shown in this lecture. Okay, because I directly want to give you the main explanation of the anomalous Zeeman effect. However, it is not difficult to obtain this expression, but for the time being, let's directly see this expression. So the Linde G factor is quite important, okay, and there are lots of questions that come from Linde G factor, okay. So now see G is the dimensionless number, okay, and for orbital motion only, as spin is taken 0 and J equals to L, and this gives G equals to 1. If G equals to 1, that will simply mean that there is only the existence of orbital motion, and if for spin motion the L is taken equals to 0 and J equals to S, and when this is substituted back in this equation, okay, in this equation, then you will get G equals to 2. That means for spin motion the Linde G factor is 2, okay. So if G equals to 1, that will correspond to the orbital motion, and if G equals to 2, that will correspond to the spin motion, okay. Now what will happen if G equals to 0? So G equals to 0, if G equals to 0 for any state, then that for that state there will be no splitting, okay, at all. And I will after some time I'm going to explain you how will be no splitting if G equals to 0, okay. So right now don't worry about it, okay. So now from equation number 3, we have the inflection energy, okay, and there you can see that at this point there is the dot product between J and B naught, and that dot product can be written like this. And here you can see that there is an angle theta. And what is angle theta? So let's see the angle theta. So theta is the angle between B0 and J, okay, and the direction of B0 is along the Z axis, okay. So this is the reason why the cosine of theta is equals to Jz over J, okay, and this Jz is further equals to mj into h naught, and that came from the quantum mechanics, and I'm not going to give you the details of this quantum mechanics for the time being. You can just keep this thing in your mind, or you can just remember it, okay, because if I'm going to give you the too much details of this, then we will divert from our current equation, from our current topic, okay. So now let's put these values back in our equation and we get this equation, okay. Now there are many things that will cancel out from this. Now the first thing that will cancel out is the J, okay, and then the remaining term can be rearranged like this, okay. Now in that equation G is written as it is. This is called quantity is called the Bohr magneton, and that is written like this, and then B naught and mj is written as it is. So this thing is now clear to you, okay. Now so in the presence of weak magnetic field, okay, the energy of the atomic state, okay, is so in the presence of weak magnetic field, the energy of the atomic state is E, and that is equals to E naught plus delta E. And let's see, so now here the E naught is the energy of the atomic system in the absence of magnetic field, okay, and delta E is the interaction energy. So delta E is the energy, is the sum of energies. So energy due to interaction between spin dipole moment of the atom and magnetic field plus the orbital dipole moment of the atom and magnetic field, okay. Now this E is the total energy of the atomic state in the presence of magnetic field, okay. Now putting the value of this interaction energy that we have already calculated, we get this equation, okay. Now since the quantum number mj has the values 2j plus 1. Okay, so its value ranges from minus j to 0 to plus j. So there are 2j plus 1 values. So we have, since there are 2j values, 2j plus 1 values of mj. Okay, so that's the reason why this energy state, so there will be 2j plus 1 energy states of the atom. Okay, so we have 2j plus 1 energy states also for the atomic system, for the atomic system, and the atom can make transition between these states. Okay, so there are two j plus 1 levels, okay, or atomic states in which atom can easily make the transition. These transitions, okay, are controlled by the selection rule, and the selection rules are here as it is as follows. Okay, so for the only those transitions are allowed for which the change in the value of mj is either 0 or plus minus 1. Okay, there is also an important point to note down, that is the mj equals to 0. The transition between mj equals to 0 to mj equals to 0 is forbidden if the change in delta, that is delta j, is equals to 0 between two states. If for two states this is 0, then there won't be any transition between mj equals to 0 and mj equals to 0. Okay, so this is an important point for you to know. Okay, now the initial, now since let's understand the, let's now we are going to find out the frequency of the line that is emitted when the atom makes the transition between two states. So let's consider the two states, so ei, initial and final. Okay, final states. So atom makes the transition between the initial and the final states. So let's so the initial level, initial energy state is written like this, and this is written with the help of our equation that I already explained you. So this, that was equation was here. Okay, so we used this equation to find, to write this initial energy state. Okay, and in the similar way we can write the final energy state. Now the atom makes the transition from the initial energy state to the final energy state here. Okay, okay, so when the atom makes the transition from initial energy state to the final energy state, the difference in energy is converted into the photon of energy h nu. Okay, and that's the Planck's law. So so the when the energy when the atom makes the transition from initial energy state to the final energy state, the difference of energy is converted into the photon, into the light photon of energy h nu, and we all know that that's the Planck's law. Okay, and now I'm going to substitute this value of ei and ef. Okay, so this is the value of ei and this is the value of ef, and I have substituted the values, and now I have just rearranged the values here at this point, and here, and this is written at this point, and this is written at this point. Okay, now this difference in energy is also equals to h nu 0, and that will be the energy of the photon if the atom makes the transition from this state to this state. Okay, so this is how this equation is written. Now I'm going to divide this whole equation by h, that is the Planck's constant. So here at this point this will be the h. Okay, so I have divided the whole equation and I got this equation. At this equation, this is the frequency. Okay, so this is the frequency of the line that you see in the Anomalous Zeeman effect. Okay, so this is the frequency of that line. Okay, when the atom makes the transition from ei to the ef, so the a photon is emitted, and that is the energy of that, that is the frequency of that photon. Okay, so now so this is the frequency of the emitted line. So now see, let's take the example to understand the Anomalous Zeeman effect. Now to explain you the Anomalous Zeeman effect, let's see the splitting of D1 and D2 lines of the sodium. So here I've shown you the sodium D1 and D2 lines. So here, so here you can see that we have taken an example to show the anomalous Zeeman effect. We are taking the splitting of D1 line and D2 lines of sodium. Okay, so this is the D1 line and that's the D2 line. So this is the D1 and that's the D2. Okay, so as I told you that this is the D2 line and this is the D1 line, and we will explain you the splitting of these lines. So if in the absence of magnetic field, when there is no magnetic field, B equals to 0, then you just see, if you see in the spectrograph, then you find that there is only one, there are only two lines. This is the D2 and there is D1 line. This will only appear. Okay, and that's the transition between this state and this state, and the other is the this state and this state. Okay, so but when we apply a weak magnetic field in this region, okay, so in this region there is the magnetic field B is not equals to 0. That means the magnetic field exists in this region. Okay, and we see that in this region what actually happens. So I have already told you what is the energy. Okay, so let me write the value of energy equals to, just hold for 1 second. Okay, so I have already explained you that the energy. Okay, so energy E is equals to E0 plus Linde G factor G mu B mg. Okay, so this in order to understand this splitting, and there is one more thing, that is B0. Okay, so in order to understand this anomalous Zeeman splitting of the lines, it is very important for you to understand this thing. Okay, this equation is very important. So when there is no magnetic field, that means if B equals to 0, okay, then this term will be 0 and the only energy E equals to E naught. Okay, so that means there will be only one energy level. Okay, that's why if you see at this point, okay, if you see at this point the value of energy is only 1. Okay, and also at this point the energy has only one value, and also at this point the energy has only one value. The reason is that B equals to 0, and because B is equals to 0, there this whole terms comes to 0. Okay, and when this whole terms comes to 0, the energy will have only one value, that is E equals to E naught. Okay, okay, so this explains that why there is no splitting at this point. Okay, so in the so in the absence of magnetic field, there will be only two lines, that is the D1 line and the D2 line. Okay, so now let's see what happens when when we apply the magnetic field. So this is the region where we apply the magnetic field. Okay, so when we apply the magnetic field in this region, okay, then if you see at this equation, okay, then in this equation you see that the B is not equals to 0. So this whole equation will exist, and that will give you the different values of this energy. Okay, so that energies will come from this from the different values of this mj. Okay, okay, so just 1 minute. So we all know that for one, okay, let me give me some time to explain you. Okay, okay, okay. Now there is an important point for you to understand is that what is in this state, this value, okay, this value is called the j, okay, and the mj will have the values from, it will have 2j plus 1 values, okay. That means here it is equals to 3 by 2, then mj will have, mj will have 2 into 3 by 2 plus 1, that is equals to 4. That means this level, when it will split, it will have 4 values. So you can see that there are 4 values, okay, okay. And these values vary from, how these values vary, so these values vary from minus j to 0 to plus j, okay. And our then that will be minus 3 by 2, minus 3 by 2, then that will be, then you, what you have to do, then you just have to add 1 to this, then that will give you just 1 by 2, and then again you have to add, sorry, okay, just hold for 1 minute, okay, that will give you minus 1 by 2, then again you have to add 1 to this, that will be 1 by 2, and then again you have to add 1, that will give you 3 by 2. So this is how you get your 3 values, okay. Sorry, this is how you got your 4 values, okay, of the level. So this is that, okay, it is written here that, okay. Now again let's come to this term, okay. So let's come to this term. So here the value of j is 1 by 2, and then the value, the mj will have 2j plus 1 values, and that will be 2 into 1 by 2 plus 1, and that will be 2. So that will give you, that means that this level will split into 2 parts, okay, as you can see that here, okay. That level will split in 2 parts, and that will start from, see, it first has 1 by 2, then you just have to start from, that means you just take minus 1 by 2, okay. Let me write here at this point, you just take minus 1 by 2, and then you add 1, you will get 1 by 2. So that will be minus 1 by 2 and 2, that will be 2 levels. So there will be 2 possible energy levels, which is written here at this point, okay, okay. So in this similar fashion, this line will also split into the 2 other lines, as you can see at this point, okay. You can see that there are 2 points, okay. This is how this energy levels is split. So as I explained you the earlier formula, that energy E equals to E naught plus G mu B mj. That is why in the presence of magnetic field B, okay, because of the presence of magnetic field B and different values of mj, you get different energy levels, and in between these energy levels atom can easily make the transition, but that transition is restricted by the selection rule. Now the selection rule is that mj, change in the value of mj should be either 0 or it should be plus minus 1. So only these levels will be allowed. So according to this level, for, so as an example to make you understand that the first level, so the first transition is this, and that can easily be possible. See the value of so let me rub something here at this point to make this board clear, okay. So for this line, what will happen is that, now see, for, so for this line, the value of mj is minus 1 by 2, and the value of mj for this level is half. Okay, so let's subtract it, 1 by 2, and this is the change in the value of mj. Okay, so finally when you solve this, you will get minus 1. So this is minus 1, and that is allowed because I already explained you the selection rule. Okay, so the selection rule was that the value of mj, delta mj, should be either 0 or plus minus 1. So in this case we have got the value minus 1. Okay, so that's why this transition is possible. Okay, so in this fashion you can find that there are 4 transitions possible from this level to this level. Okay, and again in the similar fashion you can find that there are 6 transitions possible from this level to this level, and this is how these transitions are made. And this is quite a very important question and very important answer that is usually asked in GATE and CSIR net questions. Okay, so now you have understood this example clearly. Okay, at this point, and this now completes our anomalous Zeeman effect. So thanks for watching this video, and if you like this video then please like and subscribe this video and this channel. Okay, thanks for watching. Okay, bye.